Now let's drop down again to the output from the Z-axis amplifier. Now CR4112 is reverse biased until the Z-axis amplifier gets up to 30 volts, at which time the dynamic focus circuit begins to work and corrects for any defocusing as a result of increased intensity. The 30-volt threshold is set by VR4121, and that divider composed of R4121, R4123, and R4124. Now that's an operational amplifier. Q4133 is an emitter follower driving into collector-loaded amplifier Q4137, which in turn drives another emitter follower, Q4155. Now that's the output from the amplifier, the autofocus drive, which goes up to the focus DC restorer up above, and also the drive feedback resistor R4131. RI for the amplifier then is R4125 and R4127. Notice the autofocus gain adjusts there as part of the RI resistor. The RI is compensated by C4125 and RF by a gimmick showed as kind of a dotted capacitor there just above R4131. I just kind of doubt that the dynamic focus waveform is all that critical as to require a gimmick to compensate that operational amplifier. Now we have some protective diodes. Let's begin right at the output from this dynamic focus amplifier, CR4157. Now for that we need to go up to the DC restorer and the fast coupling path through C4231. It has about 2400 volts across it. The focusing anode sets at about 2420 or so. All right, now if we short the focusing anode to ground, then we have that large positive step coupling across CR4231 and would do some damage to the dynamic focus amplifier were it not caught by CR4157 at 150 volts. Now that step certainly would turn off Q4155 and damage the base emitter junction, so that's protected by C4155. Okay, CR4137 protects the base emitter junction of Q4137 if Q4133 is pulled out of the socket. CR4129 protects the base emitter junction of Q4133 in case we lose the 150 volt supply. Now let's look at the CRT controls, the trace rotation up above. Next, the geometry adjustment. Now the mesh is tied to that adjustment, except in the limited focus very fast CRT, then the mesh is split and part of it is tied to pin 6 to reduce the background glow as a result of secondary emission. The next one, y-axis alignment, because the trace rotation doesn't affect the x and y-axis equally, so we need to correct it here. The next one is the shield volts and the astigmatism control, and then pin 9, the first anode. Notice that the CRT heater supply comes from T4201, which in turn comes from the inverter. Now the turns on that transformer didn't come out quite right in order to supply the CRT heater, so R4219 was placed in series to reduce the heater voltage a little. Notice that the CRT heater is elevated to minus 3 kV cathode potential by R4222. If those two elements of the CRT are at the same potential, then of course they don't arc over. Now let's go back to T4201. We've already discussed the top winding, the next one down, which fed the CRT cathode supply and the post-accelerating anode, and also for the CRT grid and focus DC restorers. The next one down is a full-wave bridge rectifier supplying the 150 volts, which is used on this board. And then if you look, well, right below the CRT DC Restorer, you'll notice a Zener reference 100 volt supply, which is also used on this board. The next winding on the transformer supplies the graticule lights. Now, it's a little more elaborate than the conventional wire-wound pot, but there are a couple of advantages. One, it's short-proof. That is, if you short the graticule line to ground, you don't burn up the transformer or the wire to the transformer. And then it's cheaper than the wire-wound pot and more reliable. It's just a simple half-wave rectifier with a pi filter supplying current through Q4250 to the graticule lights. Now, with the graticule illumination control, we can move the base of Q4254 from 0 volts to 6.2 volts. Now, the emitter return is to an equivalent, 210 ohms or so to a minus 570 millivolts. Now, the collector is tied directly to the base of Q4250 and will control the current through that transistor. Now, we have a couple of diodes, CR4258 and CR4256, and they straddle a current sensing resistor, R4258. Now, let's start at the anode of CR4258, call that reference. We're down a junction to the emitter of Q4254, up a junction to the base of that transistor, follow around there, down a junction through CR4256. So if everything was conducting around that loop, then we would have to have 600 millivolts drop across R4258. Well, that would take 1.8 amps in order to do that. These are only 200 mil, 6.3 volt graticule lights. So it would require a short in order to get 600 millivolts across that 0.33 ohm resistor, in which case CR4256 would turn on, would pull down on the base of Q4254, reduce the current through that transistor, which in turn would reduce the current through Q4250 and limit the current to about 1.8 amps. Now, at the time that the base of Q4254 is up to 6.2 volts, we're drawing a lot of current through, well, the equivalent resistance there, which is mostly R4257. Now, some of that current flows through Q4254, but most of it through CR4258 and through transistor Q4250. The low voltage regulators are next. That's pullout schematic 9. There we use the pre-regulated outputs from the inverter. There's 54 volts, 17 volts, and 7 volts, then minus 17 and minus 54. The outputs, and perhaps you'd like to pencil these in, plus 50 volts at about 500 milliamps. The plus 15 volts at 3 amps. Plus 5 volts at 3 amps. Minus 15 at 3 amps. And the minus 50 at about 500 mils. Now, the minus 50 volts is used as reference. There's a Zener reference at the minus 50 volt supply. But let's start in the upper left-hand corner with the plus 50 volt regulator. Now, the 50 volt sense, and in fact all of the sense inputs are taken from the motherboard, and that's the point that we want to keep regulated and free from ripple. So that when we say that we regulate to 50 volts, we regulate to 50 volts on the motherboard from which the sense is derived. Now, if it's necessary to regulate the plus 50 volts here to higher than 50 volts in order to achieve the precisely 50 volts on the motherboard, why, so be it. That's the way the regulator works. All right, the 50 volt sense comes into an error divider composed of R3214 and R3208. Notice that R3208 returns to the minus 50 volt, which is used as a reference. Now, that divider works out to precisely 0 volts at the base of Q3209B, 3209A is tied to ground, you'll notice. All right, the error signal amplified but without inversion appears across collector load resistor R3204 to drive into another collector loaded amplifier, Q3213, to drive in turn into current amplifier Q3220, which in turn drives the series regulator Q3223. Now let's see if we can get the regulator to work. Let's assume an increased current requirement. The 50 volt sense then tends to go in a negative direction. Okay, that would drop the base of Q3209B, biasing that transistor to less conduction. The A side then would conduct more. Its collector would come down, which drops the base of Q3213. Its collector would go up, fed over to the base of Q3220, would bias that transistor to greater conduction, which in turn would bias Q3223 to greater conduction, thereby satisfying the need for more current. And as we know, we will hold the 50 volt sense voltage constant under varying current requirements. Well, let's look at some of the details around this amplifier. First, the error comparator, Q3209, is a dual transistor, so that the two sides of the comparator temperature compensate one another. Notice that the base of the A side returns through 18K to ground, thereby simulating the load seen by the base of the B side looking back into the error divider. CR3209 protects the base emitter junction of the B side in case, for some reason or other, you lose the plus 50 volt output. You see that base would head toward a minus 50 volts under that condition and pop the base emitter junction. Now off the collector of the A side of Q3209, we have a diode, CR3202, and then a 5 volt zener up to plus 5 volts. Now if the 5 volt supply runs wild, that is, starts to go too high, then CR3202 will come on, which will lift the base of Q3213. Its collector will come down. That in turn will drop the base of Q3220 and shut off the plus 50 volt regulator. Now, since the plus 5 volt supply uses the plus 50, then just as soon as you shut down the plus 50 volt supply, that in turn would shut down the plus 5 volt supply. All of this to protect some circuitry out in the load. Now the collector load for Q3213 is a constant current supply provided by Q3211. Now usually that collector supply is returned to a higher voltage. However, it wasn't available here. The inverter has as its highest output plus 54 volts. There's 150 volts on the CRT diagram, but that's taken from the high voltage supply. So without the higher voltage collector supply available, the only recourse was a constant current transistor. Now we arrive at the constant current in this way. Now you'll notice the two diodes tied between plus 54 and the base of Q3211. The emitter of that transistor in turn goes through a 620 ohm resistor to plus 54 volts. Well, one of those diode junctions compensate for the junction drop from the base to the emitter of Q3211. The other diode then forces a 600 millivolt drop across R3211. Well, that's about 1 mil of constant current then flowing through that transistor to supply the collector load for Q3213. Now, right between the collector and the base of Q3213 is an RC network, which just slows down the reaction of this regulator to keep the thing from taking off in oscillation. Q3217 is the overload protecting transistor. It's a shut-'em-down circuit with a fold-back response. Now, fold-back in an overload protection circuit means that as you increase the current load after the overload circuit begins to operate, that is, then the supply delivers less current. The base emitter junction of Q3217 is across R3223. Notice the emitter ties to plus 50 volts. With 600 mils flowing, there's 1 volt drop across that resistor. However, a divider composed of R3218 and R3217 sets the base of Q3217 500 millivolts above its emitter. The transistor is cut off, or at least conducting only nanoamps. You see, some of the overload current is siphoned off through R3217. Now, as the current load is increased, the drop across R3223 increases, biasing on Q3217. As its collector pulls down on Q3220 base, it reduces the regulation current. Now, the increased load current requirements causes the 50-volt output voltage to drop. Now, that drops the emitter of Q3217. But R3217 is tied to ground. So Q3217 no longer responds just to the drop across R3223. But as the 50-volt output drops, less and less of the overload current is siphoned off through R3217. The result is fold-back operation, in which the supply delivers less current as the load current increases. The supply can be shorted to ground without any damage. Now, right between the plus 50-volt supply and the 50-volt sense is R3222. Now, that just keeps this supply from going ape if the plus 50-volt sense is lost by pulling out that plug. CR3221 keeps the 50-volt from going below ground, thereby damaging the filters, which are over on the motherboard, in case the plus 50-volt supply fails and gets shorted to one of the minus supplies. Well, let's look at the plus 15-volt supply. Remember, it delivers 3 amps. The 15-volt sense drives into the error divider composed of R3239 and R3236. Notice a return to minus 50-volt sense reference. Now, in this case, we take off across the B-side collector load because we don't want polarity reversal with this one. We have an extra current amplifier, but not an extra voltage amplifier. Okay, we drive into the base of current amplifier Q3238, which drives current amplifier Q3240, which drives the series regulator Q3241. Notice that the collector of Q3238 goes to plus 50 volts. You see, by the time we have 3 base emitter junctions in series, we couldn't supply the collector with plus 17 volts, so it's tied up to plus 50. Q3225 is a constant current supply for the collector load of Q3235B. Same configuration that we had up above. Notice that we have 2 junctions between the plus 54 and the base of Q3225. One junction offsets the base emitter junction of that transistor. The other one forces a constant current through Q3225. Now, the overload protection circuit is just a little different. The overload sense resistor is R3241 up in the collector supply of Q3241. Now, quiescently, the B side of that dual transistor is on, and the A side is off. Now, with increased current through the sense resistor, R3241 plus 17 volts stays constant, which means that the bottom of that resistor would go in a negative direction, which turns off Q3232B, which in turn turns on the A side. As its collector drops, it turns on CR3226, robs some of the current flowing through R3225. Less current, therefore, flows through Q3225. Now that drops the collector of that transistor, dropping the collector of Q3235B down below there, dropping the base of Q3238, biasing it to less conduction, which in turn biases the series regulator to less conduction. Now the divider, composed of R3234 and R3233 to plus 15 volts, provides the foldback feature of this overload protection circuit. Now you see the emitter return for those dual transistors there ties to a minus 50 volts, which won't change under an overload condition on the plus 15. However, the plus 15 will drop, which drops through R3233 to the base of Q3232B, thereby reducing the amount of current that can be siphoned off through that resistor and providing the foldback feature. R3228 and C3228 slow down the reaction of this regulator to keep it from oscillating. Notice the base emitter breakdown protection diode CR3235 around the error comparator. One capacitor I guess I missed on the plus 50 volt supply is the speed-up capacitor around the error divider. In this case, it's C3239. Right at the 15 volt output, CR3241 keeps that bus from going below ground so it doesn't damage the filters over on the plus 15 volt supply is shorted to one of the minus supplies. Well, the next one is the plus 5 volt supply. Again, a 3 amp requirement. Uses a 7 volt pre-regulated supply. The error divider composed of R3267, R3265. Now, in this case, we have a high enough supply available, plus 50 volts, compared with plus 5 volts, so that we don't need the constant current supply. So the collector load for Q3264B goes through the collector load resistor, R3246, in parallel with R3268, and is caught by CR3245 at plus 15 volts. R3245 to plus 50 volts in this case then is just a pull-up for that diode. Now the overload protection sensing resistor is R3255. Notice the foldback divider composed of R3254 and R3253, which when overload occurs will turn off the B side of that transistor, which will turn on the A side. CR3246 will turn on. That pulls down on the anode of CR3245, turns off that diode, drops off to the right there at the base of Q3258, and begins to shut down the regulator. Now all the rest is pretty much the same as the 15 volt supply. Let's look next at the minus 15 volt supply, another 3 amp requirement. Now the A side of the comparator here is referenced to a divider between ground and minus 50 volts. So we don't have an error divider as such. The minus 15 volt sense then goes directly into the base of the B side of that comparator. Now notice that the comparators so far have been referenced to ground. Okay, the error voltage is taken off across the B collector load resistor, R3277, which drives into inverter amplifier Q3285. Now the error signal, having been inverted twice and amplified, of course, appears across collector load resistor R3285 to drive to the base of current amplifier Q3290, which in turn drives the series regulator Q3294. Now, since we've inverted things here, perhaps we should go through the operation of this negative supply. Now, an increased current requirement would cause the minus 15 volt sense to go in a positive direction. It's less negative. Okay, positive going at the base of Q3275B. That collector would come down collector of Q3285 would go up, which would bias Q3290 to greater conduction, which in turn would bias the series regulator to greater conduction, thereby satisfying the need for additional current. Notice that we have two protective diodes around Q3275. Well, since we have both a minus 50 volt supply and a minus 15, either one of them could fail. Therefore, it's necessary to protect the base emitter junction of both the A and B side of that comparator transistor. Notice that the collector of the A side is tied to, well, plus 5 volts, set by VR3271. R3271 to plus 17 volts is the pull-up. Now that plus 5 volt supply, I guess we could call it, is used by the overload protection transistor Q3283. Off to the right, R3293 is the overload sense resistor. Notice the fold-back divider composed of R3288 and R3287 tied to plus 17 volts. Quiescently, the B side of that dual transistor is on, A side is off. Its collector is caught by CR3281, which in turn is tied to the plus 5 volt supply. Now that also sets the emitter level for Q3285. Now as soon as we sense an overload, then the B side of that dual transistor turns off, the A side turns on, and the collector then pulls current through R3280, reducing some of the current through Q3285. Its collector drops, which drops the base of Q3290, biasing it to less conduction, which in turn biases the series regulator to less conduction, and will begin to shut down the regulator as a result of overload. Now notice the two protective diodes to the left of the overload protection circuit there, CR3277 and CR3278. Now both of those diodes are zero biased. Now we can establish that by starting with a plus 5 volt supply. We're up a junction through CR3281 and down a junction to the base of Q3285. Now CR3277 will come on in case Q3275 turns off, that is the B side turns off, or if the transistor is pulled out of the socket. That would protect the base emitter junction of Q3285. And CR3278 comes on to limit the negative excursion of Q3285 so that that transistor can be turned off in the case of a heavy overload, direct short or such. We have two of those circuits that suppress oscillation. There's R3278 and C3278, and then off to the right there, C3289 and R3289. Now the minus 50 volt supply is very much the same, except that we have a start circuit. You see the common emitters of Q32-130, man, 5-digit part numbers. Anyway, that returns to a minus 50 volts, but through CR32-125. Now, since we need the minus 50 volt supply in order to supply the emitter, and we need the emitter current in order to get the supply to work, we need something to get us started. Well, that's over in the lower left-hand corner, where we tie into a minus 54 volts, pre-regulated, in through a 7.5 volt Zener. R32-121 provides keep alive current for the Zener. All right, initially then, CR32-123 would supply emitter current for Q32-130. Now, just as soon as the supply comes on, we pull down on the minus 50 volt supply. CR32-125 turns off the diode just to the left and removes the start circuit. Zener 32-127 is the reference for this supply, and this supply is a reference for all of the other supplies, so that's a pretty important Zener. Sets the base level at the A side of the comparator. All right, the error divider in this case has the minus 50 volt adjustment, composed of R32, 132, 33, and 34. Now that sets the base of the B side of the comparator at minus 9 volts, where it's compared against the A side. And the error voltage appears amplified and inverted across the collector load resistor R32, 117 to drive into the base of